Now let us concentrate on some interesting examples of subgroups of the symmetric group. In particular, I want to first look at the example of the symmetric group S4, so the group of permutations on the set 1, 2, 3, 4. And I want to connect it to the dihedral group of order 8, namely the symmetries of a square. And if you recall how we defined the dihedral group, it was certain permutations of vertices of the square, so the dihedral group of order 8, that can actually be realized by taking the square, lifting it off the board, doing something to it in the air, and then putting it back down. So not every permutation of the vertices of a square gives you a symmetry. In particular, if I fix the vertices which I denoted here by 1 and 2, so I denote the vertices of my square by numbers this time rather than letters, if I want to fix these two and switch the 3 and 4, which is a well-defined permutation of numbers 1, 2, 3, 4, I fix 1, fix 2, and switch 3 and 4, that does not give me a symmetry of a square, because if this side stays put, I cannot just twist the square to switch 3 and 4. It wouldn't give me the square. It would mean bending the square, and I'm supposed to just lift it, move it in the air without bending, stretching, tearing, and then putting it back down. So that wouldn't be a permutation. That wouldn't be a symmetry of a square. However, there certainly are some certainly the symmetries of the square that we studied, they are all permutations. So that means that the dihedral group can be naturally thought of as a subgroup of the symmetric group. So I would like to identify which elements of the symmetric group actually come from the dihedral group. So let's see. So if I rotate this by, so let me just write D8 here. Of course, the identity. But if I rotate the thing by 90 degrees, then what happens to the vertices? 90 degrees counterclockwise. 1 goes to 2, 2 goes to 3, right? That's the rotation like this. 90 degrees counterclockwise. 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 goes to 1. So that is what corresponds to the rotation by 90 degrees counterclockwise. What if I do the rotation r squared? So I do this twice. So 1 goes to 2 and then 2 goes to 3, so I get 1, 3. And then 3 goes to 1, right? That's a rotation by 180 degrees. So I close my cycle. Then I open up again, start with the 2. So 2 goes it goes all the way to 4. And then 4 goes to 1. So that is r squared. You can also just try to do it in the cycle notation. Write 1, 2, 3, 4 next to 1, 2, 3, 4, and then compute the cycle decomposition, and you would get exactly these two elements. What else do I get? So if I do it 3 times, so then 1 goes all the way to 4. Okay, 270 degrees, right? 4 goes to 1, 2, 3. And then what happens to 3? 3 goes to 2. And 2 goes back to 1. Okay, so that is what would be the rotation cubed. Let's look at flips now. So if I do a flip with respect to the horizontal axis of symmetry, then 1 goes to 4 and 4 goes to 1. And then 2 and 3 are also switched. So that is what I would call the horizontal flip. What about the vertical flip? Well, that switches 1 and 2. And then switches also 3 and 4. Finally, there are these two diagonal flips. So that flip fixes 2 and 4 and switches 1 and 3. So that's just 1, 3. Right? So that is this diagonal flip, while the orange one is the vertical one. And finally, the last one is this flip. So that fixes 1 and 3 and switches 2 and 4. Okay? So that gives me D8 as a subgroup of S4. Note, it's got 8 elements, of course, as the D8 should, and these permutations represent the symmetries of a square. I encourage you to identify D6 as a subgroup of S3. Okay, exercise. And you will notice something interesting. Okay, so one subgroup of D8 of S4 is the dihedral group D8. If you number these vertices like this, right? I mean, I could sort of number them differently. I could have numbered them differently. I could have said 1, 3, 2, 4. For some reason, I don't know. It would be just like that. And then you would get actually different permutations. Okay, so that's sort of different ways to represent D8 inside S4. But here's one of them. Some other group. Okay, so D8 can be thought of as a subgroup of. So maybe I just write here a little conclusion here. So conclusion. D8 can be realized as a subgroup of S4. And let's look at some other group that doesn't seem to have anything to do with the symmetric group. Namely, so another example, let's look at the group of fifth roots of unity. So remember that consists of, that's actually a cyclic group, right? Generated by zeta 5, where zeta 5 is cosine 2 pi over 5 plus I sine 2 pi over 5. And I'm going to think about it in a certain way. So let's draw this regular pentagon. Maybe, yeah, well, maybe here. So 1, I, in a circle. And inside the unit circle, you have, so it's zeta 5, zeta 5 squared, zeta 5 cubed, zeta 5 to the 4th, and here's 1, of course. And so, if I connect it, I get a, doesn't look so good. I get a regular pentagon. Okay, maybe a little better. I had to cheat the picture a little bit to get it to look like a regular pentagon. Okay. So normally, of course, these are just these roots of unity. So the vertices of this regular pentagon, that is the group mu5 under multiplication. But I'm going to realize it in a slightly different way. Namely, note that okay, so first, before I do this, let me number the vertices. Right? I'm going to number this one here 1, just like that. I'm going to number this one 2, 3, 4, 5. You might have said, oh, why don't you maybe just number them as the powers of the zeta? I could have done that as well, but I kind of like to have numbers 1, 2, 3, 4, 5 because I'm thinking about the symmetric group already. So note that multiplication by zeta 5 induces a rotation by 72 degrees counterclockwise on the pentagon. So what do I mean by this? So I'm going to take every vertex and multiply that vertex in terms of complex numbers by zeta 5. So if I do 1 times zeta 5, then what do I get? I get zeta 5. So times zeta 5. 1 times zeta 5 is zeta 5. Zeta 5 times zeta 5 is zeta 5 squared. Zeta 5 squared times zeta 5 is zeta 5 cubed times zeta 5 is zeta 5 to the 4th, and again times zeta 5 get me back to 1. So when I think about this, multiplication by zeta 5 gives me a rotation of this pentagon. So it sends vertex 1 to 2, vertex 2 to 3, vertex 3 to 4, and vertex 4 to 5, and vertex 5 to 1. So it induces permutation. So a permutation on the vertices equal to 1, 2, 3, 4, 5. What about multiplication by zeta squared? Zeta 5 squared induces a what? If I multiplied it by square of zeta 5, then 1 would go all the way here. This guy would go all the way here if I multiply by zeta 5 squared. This, if I multiply by zeta 5 squared, it would get me here. Zeta 5 squared. And so on. So it's a rotation by 180 degrees. What did they say? 144 degrees. Counterclockwise. So a permutation. 1 goes to 3, 3 goes to 5, 5 goes to 2, 2 goes to 4. And so on, right? In particular, this actually is the square of this one. So multiplication by zeta to the n would give me zeta 5 to the n induces a permutation 1, 2, 3, 4, 5 to the n. So again, I can think of the elements here as permutations. 1, multiplication by 1 does nothing. Multiplication by zeta 5 rotates this by 72 degrees, so it induces this permutation. Multiplication by zeta 5 squared induces that permutation, and so on. So, in that sense, I can think of, let me erase this big picture. So this realizes mu5 as a subgroup of S5. Really of D10, which then can be thought of as a subgroup of S5, right? Because these were just rotations. In this case, we can use sort of a fancier language, because while I define sort of my dihedral groups as certain permutations and vertices, definitely mu5 is not defined that way. I had to do some mental acrobatics to see it as permuting something. So what's the proper mathematical way of expressing this idea? that I can realize some group as a subgroup of S5 or S4 or and so on? Well, we can use our friend the homomorphisms. Namely, so I can construct, so more precisely, there is an injective homomorphism let's call it phi, for lack of a better word, better letter, from mu5 to S5. Oh, you know, this is really helpful because I know that mu5 is a cyclic group and I know how to construct homomorphisms from cyclic groups. First of all, I just have to tell you where the generator goes. So it's enough to just tell you where the generator goes. And I already have my candidate. I sort of feel really good about it because multiplication by zeta 5 should be that permutation. So I'm going to send zeta 5 to that permutation. But mu5 is a finite cyclic group, so you know that I cannot just choose whatever I want to send my generator to. I have to make sure that the order of this divides the order of the group. So note, the order of 1, 2, 3, 5, 1, 2, 3, 4, 5 needs to divide the order of mu5. All right, but what is this? This is 5. What's the order of a cycle of length 5? You know what it is. It's 5, 2. So this is actually 5 as well. Right? So I said this is necessary, but I'm just noting it that indeed 5 divides 5. So this divides that. So there is such a homomorphism. So there is an injective homomorphism. Well, this only proves that there's a homomorphism. Why is it injective? Well, you can just sort of do it by inspection, that it's an injective homomorphism, but clearly the kernel of phi would be which powers of zeta will be mapped to the trivial, to the do-nothing permutation. I already know multiplication by zeta 5 rotates the thing by 72 degrees, zeta 5 squared by 144, so the only thing that rotates it by nothing would be the rotation by 0, or by 360, which is the same as rotating by 0, and so on. So that is just, the kernel of it is only 1, multiplication by 1. Okay, and what do I know about homomorphisms? So, the image of phi is a subgroup of S5. And phi can be thought of as an injective homomorphism that surjects. Well, it doesn't surject onto S5. The order of this is 120, and the order of the image is only 5, but it surjects onto the image. So, mu5 is isomorphic to the image, because it's a bijective homomorphism to the image. So, and that is a subgroup of S5. So the way we say it is mu5 is isomorphic to a subgroup of S5, i.e. mu5 is isomorphic to a subgroup of S5. Okay, this is just two examples. This is just two examples of some quite important theorem in the theory of groups, which I'm going to state only, but not prove. But it should maybe give you the idea of the importance of the symmetric groups. theorem, every finite group is isomorphic to a subgroup. Of the symmetric. So in some sense, every finite group can be thought of as living inside some symmetric group. So if you wish to take that angle, and I do not encourage you to take that angle, you could say that in order to study finite groups, it's enough to just study the symmetric groups, because every finite group somehow lies inside the symmetric group. I do not encourage you to take that angle because you sometimes want to know where the groups actually came from, rather than they can be realized inside S5. Sometimes I want to think about the fifth root of unity as just fifth roots of unity, rather than rotations of a regular pentagon. However, this gives one reason why symmetric groups are important. Second reason why symmetric groups are important is that you see that we've looked at symmetries of a square. Now symmetries of a regular pentagon came in. Generally, symmetric groups tell you about symmetries of various objects. Now, they don't have to be these rigid figures, because otherwise you'd say, oh, dihedral groups are enough to study symmetries. Yeah, if you study symmetries of a square, regular pentagon, equilateral triangle, and so on, then yes, dihedral groups are enough. But sometimes you want to study other symmetries, symmetries of other objects that are not necessarily geometric objects, or not such simple geometric objects. And then again, symmetric groups play a major role. One type of such symmetries that you might want to study, that people do study, are roots of polynomials. That ties back to our entire large chunk of the course where we studied fields, field extensions, polynomials, and their roots that lie in these field extensions. The study of symmetries of roots of polynomials leads one to study the so-called Galois theory. And Galois theory leads to sort of our best understanding of symmetries of roots of polynomial equations, and in general understanding how to solve and when can you solve polynomial equations. We're not going to talk about this here, but this is yet another reason why symmetric groups are so important. And in fact, that's one of the contexts in which groups arose historically.